All right, so you've gotten a little bit of time to work on these. Let's run through and see if we were able to figure these out, okay? So what did we get for A? What did we get for A? 3, good. A constant function always equals the same thing. So no matter what you're approaching, it's going to approach that value. How about the line y equals x for number B, or part B? Negative 4. Okay. C? 2. Now how did you get 2? Okay, you graphed it and you traced it. And you did direct substitution. You could trace and you could do direct substitution because you recognized that it was continuous, right? Around the value 3, we didn't have any jump or asymptote there. So we could do direct substitution, and we got the cube root of 8, which was 2, okay? Now, another way I know that this is continuous even without using my graphing calculator is notice we have a composite function here. We have a cube root function, and inside of that is a quadratic function, okay? And the quadratic function we know is continuous. The cube root function, you may or may not have had as much to do with that one, but that one is also continuous. So if you have a continuous function inside of a continuous function, the result is going to be continuous. So as we're approaching 3, we can do direct substitution. Now, we'll take a moment here and take a look at this limit theorem at the bottom. Okay? This says here that if you have a composite function f of g of x that you're trying to take the limit of, you can simply take the limit of the inside function, that's what this is doing right here, and then evaluate the outside function for that. Okay? So in other words, I could rewrite C like this, okay? I could rewrite this as the cube root of the limit as x approaches 3 of 2x squared minus 10. And then I would say, okay, well I know that parabolas are always continuous, so that I know for sure I can do direct substitution with. I do that and I get 8. And then we're back to, okay, now the cube root of 8 is 2. So there's kind of 2 ways you could have thought through that one in order to figure it out. Okay? All right. Now, tangent. Here's where it's helpful to remember your trig and your graphing. Okay? The tangent function, if you recall, has asymptotes at negative pi over 2 and at, well, sorry, I did that backwards, pi over 2 and negative pi over 2. And in the middle it looks like this. Okay? Well, that's continuous right around the origin there, right around 0. So as x approaches 0, I can simply evaluate tangent of 0, and tangent of 0 is 0. Okay? So there's my solution for that limit. Okay. Now E, what'd you get for E? Negative pi. Okay? Negative pi. Now how did you come to that conclusion?
If x approach pi, cosine x approach negative 1, then negative 1 times pi is negative pi.
All right, great. And he just used a property of limits that we can use as well. When you have a product, you can take the limit of one factor and multiply it by the limit as x approaches pi of the other factor. Okay? So, as x approaches pi, x equals x, or x equals pi. And you guys know that cosine is continuous for all real numbers. So cosine of pi does equal -1. Remember our unit circle. So that gives us negative pi. Okay? All right. Now it may have been a while since you used your unit circle, but you got to review it if you don't remember. Okay? All right. So that's a good little warm up here. Make sure we understand here, and introducing one additional theorem that we can use when evaluating limits of composite functions. Okay?
But if you do E on the graphing calculator, how do you find the
All right, so looking at the graph here, you can see that, well, it looks a little different than our cosine graph. We do have a continuous function. Okay? So as we're approaching pi, this is where, it's helpful to use your calculator a little bit. Let me do this. Okay. Obviously, my graph is not labeled in terms of pi, but let's see here. 3 is right here, so 3.14 is going to be somewhere around here. And by the way, this is a good evidence of our limitations that we've got. Okay. And then here's -3. -3.14 is going to be somewhere around here. Okay. So if you looked at the graph and you said the limit was -3, I can get that. Okay. But again, that kind of shows us the limitation of using our graph. But it at least gives us a good idea of where it should be. That's okay. All right? Okay. So, today's focus is what we call the squeeze theorem. This is one of those theorems that sounds a lot more complicated than it actually is. Okay? The squeeze theorem. You see here this diagram over here that's, and we have 3 different functions. But let's read this here. It's good for you to see and hear the notation being read to get used to it. And then we'll explain. It says if the function f of x is between h of x and g of x inclusive, that's what the equal signs are there for all x's in an open interval containing c, except possibly at c itself, and if the limit of h of x as x approaches c, and the limit of g of x as x approaches c both equal L, then the limit as x approaches c of f of x exists, number 1, and is also equal to L. Okay? Now, probably all of you are like, okay, what does that even mean? All right? What does that mean at this point? This is where a picture is far more valuable. Okay? So let's look at the picture closely. Okay? So, we have this function. I'm going to make this a little bit thicker so we can see it a little better. Here we have this function g. I'll highlight this in red. And it may or may not exist right at c. We may have a hole there. But notice if I were to travel along g from both sides, the limit would be whatever this value is. Okay? So here we have the limit, and we'll call that the value L. Okay? So notice g, as we approach this value c, has a limit equal to L. Everyone follow that so far? Yes. Okay. Now, let's look at h. H is down here. And it's going along. It also may or may not exist here, but then goes along this way. Okay? Now, what would the limit of h be as we approach c?
Same as G.
Same thing, okay? It's also L. Right? Yeah, that didn't turn out too well. Okay? It's also L. So, then we have this function f. F, at least for this interval that we're looking at here, goes here, and then continues on. Now, what do we know about f, at least for this interval, when it's compared with f and g? Or g and h, sorry.
It's in between them both.
It's always in between them. Okay? Now, it's possible that f could come up and actually touch one of them, but it'll never go above. Okay, that was one of the parts of the squeeze theorem. It always has to be between or equal to those two functions. Okay? Now, we can see here g is approaching this value L. At the same time, h is approaching this value L. Okay? And this is kind of like Le Cafe on Chick-fil-A Day. When you've got all these high schoolers coming from here and all these high schoolers coming from here, and then you have the poor middle schoolers who made their way over, and what happens to them? They get squeezed, right? Okay? So you have all these coming, and they're all headed for the same value right here at L, and this has to stay in between them, and as a result, it gets squeezed right into L as well. That's what the squeeze theorem is telling us, okay? If we know for a fact that this will always be between them, and this goes to L, and this goes to L, then F has to go to L as well. Okay? That's the squeeze theorem. Whole lot easier to understand once you see it than just reading the notation. Okay? We're actually going to use that in a minute here to prove a couple of properties or common limits here, as you can see down below. Okay? Before we get to that though, does anyone have any questions about what we've just observed? Okay? Alright, so there are two pretty common trig limits that appear on the AP exam relatively frequently. I recommend that you memorize these because as you'll see, the development of them or the derivation is probably not going to be something you'll remember if you don't remember what it equals anyways. Okay? We're going to actually derive this first one here. Okay? But it's the limit as x approaches 0 of sine of x over x will equal 1. Now that happens because of the squeeze theorem. We'll see that in a sec. But if I were to just plug in x equals 0, we'd get 0 over 0. Okay? So that's indeterminate form. It's undefined. We got to do something else with it. There's no way to factor it and get rid of that whole. So we're kind of stuck, except for with our squeeze theorem. The other one we're not going to prove here, but the limit as x approaches 0 of 1 minus cosine over x will equal 0. Okay? So, let's take a quick look here at using the squeeze theorem. And we're actually going to use the unit circle to prove this. Okay? Now, let's state what we're trying to prove here. We're trying to prove that the limit as x approaches 0, or actually I'm going to use theta because that's the notation. That's the notation that's used here in the proof. so instead of x, I'm just using angle theta, of sine of theta over theta will equal 1. That's what we're trying to prove here. Okay? So, let's take a quick look at this diagram we have. We have the unit circle and we have 3 different triangles, or actually 2 triangles and 1 sector that we're going to focus on. Okay? First of all, you guys know from pre-cal honors that the unit circle has a radius of 1, so that's why this side right here is 1. And you know that every point on the unit circle has coordinates equal to the cosine of the interior angle and the sine of the interior angle. Our interior angle here is theta. So we have this triangle right here. Okay? And I want to look at the area of this triangle. Okay? The area of this triangle, any triangle, is 1/2 base times height. Well, what's the base of this triangle? 1. What's the height? Yeah, there we go. The height is the sine of theta. Okay? That's the sine of theta. So you can see over here, we've illustrated this like this. Okay, here's that red one, just so we can make the connection color coding. So the area then, 1/2 base times height, it's 1/2 times the base 1 times the height sine of theta. And that's how they get sine of theta over 2. Okay? Okay? Do you understand that? Not quite? Okay. Do you understand where we're getting the sine of theta as this height here? Because that might be the part that... Okay. Again, that's because that corner of the triangle is this point on the unit circle. Okay? And the y coordinate is how high it would be.
Actually, I think we don't need to calculate we don't need to put in the area of the triangle. Look, 怎么会这样？哦，来自于它。
We don't... What are you trying to...
Right. Then,
Well, we're gonna get to that triangle in a second.
wait, just let me explain.
Okay.
社会结合那个好比。
All right, so let's now look at that larger triangle, okay? Now, we have constructed this by extending this radius out past the circle, okay, until we have now formed a right triangle in that way, okay?
I have a question.
Yes.
Then why we need to calculate the area of the triangle? What's the purpose of that?
You'll see. We're getting to it.
Okay.
I promise.
Okay.
Okay? So, the y coordinate there is going to be the tangent of theta, okay, which we would have to derive, all right, but we'll just go with that for time's sake. Okay? So that's what this triangle is represented here, okay? The base is 1, the height is tangent. So again, area is 1/2 times the base times the height. Okay? So that's tangent of theta over 2. Okay? Once we simplify that. Okay? Now, the area of a sector, okay? Stay with me here. The sector we're talking about is this right here. This is why we're dealing with areas, okay? How would you compare the area of that sector to the areas of the red triangle and the blue triangles?
Between them.
The area is going to be between the two areas of the triangles. Okay? Aha, now it's coming together. This is why we're doing this. Okay? Whoever did this first, it wasn't this easy for them. Okay? We have the benefit of knowing that this part works. Okay? I'm not sure how in the world someone came up with this to try to prove it, but it works. It's pretty cool. Now, you may not remember how to find the area of a sector, so real quick, let's just derive the area of the sector here. Remember, there's a proportion. The central angle divided by the full 2 pi of a circle will always equal the area of the sector divided by the total area of the circle, which is pi r squared, right? In a unit circle, what's the radius? 1. So what does pi r squared equal? Just pi. It's pi times 1 squared, so it's just pi. Okay? Now, if I want the area of the sector, I need to now multiply by pi to get the area of the sector by itself, and that cancels. That'll cancel as well, and you'll notice that's where we get the theta over 2 from. Okay?
Wait, so it's theta over 2 pi is equal to area of sector, all of that stuff, and then you just cancel it out?
Yes.
Okay.
Okay? Now, here's where you've got to know where you're trying to go in order to be able to manipulate what we have to get there. Okay? Right now we have this 3-part inequality. The area of the sector is between the areas of the 2 triangles. Okay? So what we're going to do next is we are going to multiply all of these parts by 2 over sine of theta. Okay? 2 over sine of theta. And times 2 over 2 over sine of theta. Okay?
Wait, why do we do that?
This is the part where we know we're trying to get to having sine of theta over theta. And by doing this, our middle will end up being at least the reciprocal of what we're trying to get, right? Because the 2's will cancel. And notice what we end up with. Tangent over 2 times 2 over sine. The 2's cancel. And tangent, remember, is sine over cosine. And if I'm multiplying it by something over sine, then the sines will cancel. And that's how I get the 1 over cosine. Okay?
Mr. Nixon?
Yes.
Where'd you get the 2 over sine from? Oh, because you're multiplying, so you, or,
Yeah, I just, we did the 2 over sine because that'll actually make the right-hand side all equal 1. And it'll make the middle be close to what we're trying to actually get.
okay, so you multiply them all by the same.
We're multiplying them all by the same thing, okay? To keep the inequality proper, okay? Now, just stay with me real quickly here. At this point, now I can take the reciprocal of all 3 parts,
Why reciprocal?
okay? Well, I'm taking the reciprocal because what we're trying to prove is that the limit of sine of theta over theta. Now I've got what we're trying to prove. And here's where the squeeze theorem comes in, okay? What is the limit of cosine as theta approaches 0? It's 1. Cosine of 0 is 1, right? What's the limit of 1 as theta approaches 0? 1. So if both of these approach 1,
So it's also 1.
then we know that the limit of sine of theta over theta is 1. Okay? They squeezed it in, so now we know it has to equal 1. Okay? Alrighty. Good work, guys. We'll see you tomorrow.